looking at impacts, and specifically when I say impacts, I'm looking at streamflow magnitudes in a particular season or total carbon, or vegetation carbon, but it's also possibly transferable to other sorts of impacts for evaluating changes. And there's a lot of practitioners and resource managers at this conference that hopefully can benefit from a tool such as this, and I'd be interested in talking with those people further and getting feedback. So the motivation of this work is really, there's a lot of climate information out there. Lots of global climate model output is now available. And here's a list from 2013. But throughout the conference, we've heard of all these different models. And in addition, there's different emission scenarios and different runs for each model. And all of this information is great and has really helped us to better understand the climate system. But if you're a practitioner and you have limited resources and you want to integrate climate information into your planning, and you're not a climate scientist, you look at this and it's quite overwhelming and makes you kind of want to pull your hair out. So what we're looking at is hopefully providing guidance in looking at ways to defensively select certain models to use for more publicly scrutinized decision making. So can we provide guidance to people looking at impacts assessments that includes not just changes in temperature and changes in precipitation, but also is a more bottom-up approach that accounts for the impact. And so essentially to address this frustration, we're looking at identifying subsets of global climate models that are first good performers. So this gets back to the question at the end of the last talk, a ranking of meaningful models that adequately simulate historical climate, providing plausible results for the region of interest. So throwing out those wild models and focusing on the good performers. And then second, looking at models that span the range of possible futures for the variables that are most important to the impact under investigation. And so an example would be in the Willamette River Basin, looking at flows for fish in the summer months. And you want to get the models that are good performers, but also the models that capture the plausible higher flows and the plausible lower flows. And so we're going about doing that, looking at good performers. Here is the paper that Phil just talked about. David led an effort to look at global climate model rankings for the Pacific Northwest. And so we have a list of models and a relative ranking that we can employ in this analysis. And then second, looking at spanning the range of possible futures. And what is typically done if you can only select a certain number of models is you might look at a scatter plot of the changes in temperature and changes in precipitation of the different global climate models, and then maybe look at selecting ones that are warmer and wetter or less warm and drier, and kind of spanning the space in that way using just the changes in temperature and precipitation. But what we were really interested in is taking this a step further and really looking at what are the impacts that are being evaluated and more tailoring the approach to assess that particular impact. And this idea kind of evolved from some work that I've been doing in the past couple of years looking at hydrologic sensitivities. When I say hydrologic sensitivities, what I mean is how much, if you change the temperature, how much do you change the stream flow? Or if you change the precipitation, how much do you change the stream flow? And we've gotten at this using models, and we use the variable infiltration capacity model for these particular figures, but it's simply running the model through the historical period and looking at what the stream flow is, and then running the model again where all you do is change the temperature by 1/10 of a degree, and then look at the difference in stream flow from that 1/10 of a degree temperature change, or a 3-degree temperature change. How much does that then change the stream flow. And the same concept with precipitation. So if you run the model just historically and then run the model where you've changed the precipitation by 1%, how much have you changed the stream flow? And from that, in these previous studies, it started in the Colorado, but then I also moved some of the work to the Pacific Northwest. We could use these temperature sensitivities and precipitation elasticities as a back-of-the-envelope approach to getting at what stream flow change might be. So using the temperature sensitivity multiplied by the change in temperature from the GCM, adding that to the precipitation elasticity multiplied by the change in precipitation from the GCM. And the precipitation elasticity and temperature sensitivity are functions of the increment of change that you're using to calculate that, and I'll explain that a little bit more in just a second. So to start out with, we looked at impacts for seasonal stream flow, and we looked at this in 3 different locations. They were 3 different locations that have a variety of different hydrology. So the Columbia Basin, which is more snow dominant, and the management focus was more on the spring snow melt, so focusing on April through June. We also looked at the Yakima, where we focused on the irrigation season, which is from April through September, and the Willamette, where we focused on summertime flows, so June, July, and August. And I'll give examples of results for how in each of these basins we set up the context for selecting GCMs. And so now when I talked about the temperature sensitivity being a function of the temperature change, this is really what I was meaning. So first, the perturbation that I did in the hydrologic model was 1/10 of a degree change. And here this green dot indicates that if I change the temperature using an increment of 1/10 of a degree, I change the stream flow. I decrease the stream flow by 18% per degree C. And now if I use an increment of change of 3 degrees and do that same calculation, I actually don't decrease it as much. And then 6 degrees, I don't decrease it as much per degree. So essentially, the reason for this is the larger your temperature change in the Willamette, the more you're reducing the snow. And so per degree, you're actually not getting as large of a change. Overall, you're getting an overall larger change from the larger temperature change, but per degree, it's less. And looking at these in the Yakima and then also in the Upper Columbia, part of the reason you get differences in these lines is you're looking at different seasons. But the take-home message of this is you're getting nonlinear temperature responses. And then we did the same experiment using changes in precipitation, where we changed the increment of change used to calculate the sensitivities for precipitation. And here you're getting more of a linear response, where it doesn't matter what the increment is, you end up getting the same per percent change for precipitation, which actually simplifies the calculations a little. Although if it wasn't linear, you could also do the same evaluation. So going back to selecting global climate models, now instead of just looking at the changes in temperature and changes in precipitation, we can go back to that simple calculation of streamflow change and just draw contours of plot the curves of constant change on this figure. And here's looking at it for the Yakima for the irrigation season. And so here you can see that there are some models that show you're getting a pretty large decline in the summer. And there are models that you're still getting a decline, but it's not as large. And so you can use this type of information to then say, okay, I can only select 3 models. And so I want to get a model that is very dry, and one that is less dry, and then one that's somewhere in the middle. And you can also use this in combination with the rankings to look at the contours and select the highest ranking model within that contour of change that you're hoping to see. And so this is a way of going about selecting global climate models that has a little more rigor to it in regards to the particular impact of interest. And so we looked at this for 3 different basins, as I mentioned before, and as you can see, depending on the basin and depending on the time period of interest, you do get different shaped contours. And in addition, so this is that equation I was talking about. You can also use this to just do a really quick and dirty poor man's approach to seeing what the changes you're getting from all of the different global climate models. So this is really computationally savvy in that to calculate the sensitivities, you're doing about 9 different runs with your impacts model to assess what that space is, but then you can apply the changes in temperature and changes in precipitation from the global climate models to get a sense of what the probability distribution function is. And again, this is a very simplified approach and kind of giving you the back of the envelope of what those changes might be, and intended for if you want to just get a general sense of what changes are and do something like compare what the different RCP values might be for these different basins, or you could also use it to select models for further investigation. As I mentioned, we looked at different impacts, so streamflow was one, but we also wanted to see if we could do this with a different impact, so we looked at total vegetation carbon in 3 different ecoregions. And for the sake of time, I'm just going to highlight that we did this, and again, you see that the responses differ depending on the different ecoregions. Here you're just looking at annual changes, so you're not changing the seasonality. And here in some places, the change in precipitation doesn't really matter, whereas in others, the more drier regions, the precipitation change has an effect. And then again, you can also look at the probability distribution functions as well. So with that, I just want to conclude by saying generally this approach allows us to guide GCM selection rather than just using the temperature and precipitation changes. You're kind of starting at what are you going to use these models, what is the question you're asking of these models, and then select models that span the space of that particular impact. Again, it's computationally efficient in terms of getting that back of the envelope value. You can run 9 different models and then apply those changes to GCMs. And here those PDFs were 140 different GCMs. And so running each of those individually to compute what the changes would be a lot larger effort. And so it's nice to be able to get a quick sense of what you would expect the results to be before launching into the larger effort. And in hopes that by being more specific in how you're selecting which runs you're doing, you'll have more time to look at the underlying processes and evaluate that, freeing up resources. So you're providing something that's defensible for decision making, yet you have more resources available to really understand your results instead of just doing all this data processing. And then also it provides both qualitative information like the probability distribution functions, and then also information for more technical evaluations. So it's useful for practitioners, but it's also useful for people who are doing the more rigorous technical evaluations as well. And then also it's transportable. Here we've shown this type of approach could be applied to 2 different impacts, but it could possibly work for others. And we've only used one hydrologic model and one vegetation model, but it could be used with multiple different hydrologic models or whatever vegetation models or whatever your impact model is. And in doing this, you want to make sure that you abide by checking what the linearity is and also how temperature and precipitation changes interact. So you want to make sure that you're doing it in a way that you're not you want to be careful about how you do the analysis, but in being careful, you can also get at some of these results more quickly. And with that, I'd like to acknowledge funding sources and ask for questions or feedback. I'll try to remember. Remind me if I don't.
We have time for 1 to 2 questions.
Go ahead. Yep. Oh, I'm sorry. I was. Yeah. I mean, it is a question of what is computationally efficient, and I think the idea here is to start with the impact so you really understand what that impact is that you want to get at, instead of just saying, well, these models work everywhere for every impact. You're defining what that impact is and understanding that. But again, I've had advice on ways that you could even make this more intricate and not just this simple linear. And my response is you end up doing more runs to get at that than you would if you did just kind of the full approach as it's been done before. But in terms of if you define the impact and that's really what you're interested in, then looking at just so, for instance, this approach got started by a request from the Willamette Basin saying we want to select just 3 different models to do further analysis on, and we're really interested in flows for fish in the summertime. And so this was a quick way to evaluate that, whereas if you would have gone further, it would have taken a lot longer.